Chapter 10, Surgical Instrumentation. Welcome to the comprehensive audio guide for Chapter 10, focused on surgical instrumentation. This is one of the most critical technical chapters in your training because surgical instruments are the primary tools used by surgeons to perform life-saving procedures. They represent the physical connection between the surgical team and the patient. Consequently, these instruments are among the most expensive and essential assets in any healthcare facility. It is not uncommon for a single facility's inventory to cost millions of dollars. As a sterile processing technician, you play a pivotal role in the management and protection of these high-value assets. Your primary responsibility regarding surgical instruments is to serve as the ultimate quality control checkpoint. You must ensure that every device leaving your department is clean, sterile, functional, and immediately available for patient care. This requires a deep, professional understanding of instrument anatomy, proper usage, and the ability to identify even the slightest damage or malfunction. While the selection of specific instruments for a procedure depends on the surgeon's personal preference and the surgical specialty, the inspection process is universally the responsibility of the sterile processing technician. There are three main pillars supporting your role in instrumentation. The first and most important is patient safety. The ultimate goal of every inspection you perform is to protect the patient. You must remember the foundational rule that an instrument that is not clean cannot be sterile. Furthermore, an instrument that does not function properly, such as a scissor that tears tissue rather than cutting it, can increase operative time and surgical risk. The second pillar is asset management. Proper handling and rigorous inspection extend the useful life of the instruments. By identifying problems early, you reduce the frequency of costly replacements, thereby saving the facility significant financial resources. The third pillar is the standard. To function effectively, you must know what a healthy instrument looks and feels like. You must memorize the standard appearance and mechanical action of each tool so that you can instantly identify one that is broken, stiff, misaligned, or dangerous. To perform effective inspection and assembly, the sterile processing technician requires a dedicated and properly equipped workspace known as the instrument workstation. The physical environment directly impacts the quality of the inspection process. There are four critical components to a compliant workstation. First is lighting. The workstation must have adequate overhead lighting to provide general illumination. However, this is not enough. A focused, adjustable task light is essential. You need this directed light to peer inside narrow internal channels, inspect the depths of jaws, and check box locks for debris or cracks. Second is magnification. A lighted magnifying lamp, commonly referred to as a diopter, is required for every inspection table. The naked eye is often insufficient to catch the early signs of failure. Magnification is necessary to identify microscopic cracks, pitting, minute debris, or damage to cutting edges that would otherwise go unnoticed until they failed during surgery. Third is ergonomics. Because instrument inspection is repetitive and physically demanding, the workstation should be ergonomically designed to prevent technician fatigue and injury. This includes adjustable chairs to support the back, anti-fatigue mats for periods of standing, and adjustable table heights to maintain focus and physical health throughout a shift. Fourth covers supplies. The station should be fully stocked with necessary testing materials so you do not have to leave your desk. This includes sharpness test materials like latex and index cards, lubrication, often called instrument milk, tip protectors, and labeling supplies. Now we move into the science of the instruments themselves, starting with manufacturing materials. Most high-quality surgical instruments are manufactured from stainless steel. It is important to understand that stainless steel is an alloy, which means it is a mixture of metals. It is composed primarily of iron, carbon, and chromium. The specific quality and type of stainless steel used determine the instrument's function and durability. The first major category of steel is the 400 series, also known technically as martensitic stainless steel. You must remember this term. The defining characteristics of the 400 series are that it is high in carbon and low in chromium. Because of the high carbon content, this steel is very hard and can be heat hardened or tempered to hold a sharp edge. Crucially, the 400 series is magnetic. However, there is a trade-off. While it is hard and strong, it is more prone to corrosion than other types if not properly maintained. Therefore, the 400 series is used for instruments that must cut, bite, or require strong gripping jaws. Common examples include scissors, osteotomes, chisels, rongeurs, and the jaws of hemostatic forceps. In contrast to the harder 400 series, the second major category of stainless steel is the 300 series, technically known as austenitic stainless steel. The chemical composition of this series is distinct because it is high in chromium and low in carbon. This specific balance of elements creates different physical properties. The 300 series is softer and more malleable than the 400 series, meaning it can be shaped more easily but cannot hold a sharp cutting edge. However, its greatest strength is that it is highly resistant to corrosion and rust. A key identifier for the technician is that the 300 series is generally non-magnetic. It is important to note, however, that it may become slightly magnetic after being worked on or machined, but this is minimal compared to the 400 series. Because of these properties, the 300 series is used for instruments that do not require a sharp edge but need structural strength and longevity. Common examples include retractors, suction tubes, specula, rib spreaders, and hollowware items like surgical bowls and basins. Beyond stainless steel, some specialized instruments are made of titanium. Titanium offers unique advantages in the operating room. It is a non-magnetic metal, which makes it safe for use in MRI-compatible instrument sets. Physically, it is extremely lightweight yet incredibly strong. This reduction in weight is critical for microsurgery instruments, as it significantly reduces hand fatigue for surgeons performing long, delicate procedures. Visually, titanium is easy to identify because it often has a distinct blue finish. This blue color is the result of an anodizing process and helps the sterile processing staff instantly distinguish titanium instruments from stainless steel ones during assembly. Once the material is selected, the instrument goes through a complex manufacturing process. It begins with forging, which is the process of heating the metal and shaping it into a rough form. After shaping and polishing, the instrument undergoes the most critical chemical step known as passivation. You must understand this process thoroughly. Passivation involves treating the stainless steel instrument with a chemical solution, typically nitric acid. This acid attacks the surface of the metal and removes foreign iron particles that may have been deposited during machining. The result of this reaction is the formation of a transparent, protective film called chromium oxide. This chromium oxide layer is passive, meaning it is non-reactive. It creates a barrier that shields the inner base metal from corrosion, rust, and oxidation. The maintenance of this passive layer is a daily responsibility. Interestingly, normal handling and routine steam sterilization actually reinforce this layer over time. However, it is fragile. Harsh chemicals like saline or bleach, improper handling that causes scratches, or the prohibited practice of engraving an instrument can strip this layer away. Once the passivation layer is damaged or broken, the steel underneath becomes immediately susceptible to pitting and rust. The final stage of manufacturing is the surface finish. The type of finish applied affects how the instrument is used in the operating room and how it impacts the surgeon's vision. There are 3 primary finishes you will encounter. The first is the shiny or mirror finish. As the name suggests, this finish is highly polished and reflective. From a processing standpoint, it is beneficial because it is highly resistant to corrosion, and surface defects or soil are very easy to spot. However, in the operating room, it presents a challenge. The mirror surface reflects the bright surgical lights, which can cause significant eye fatigue or blinding glare for the surgeon. The second is the satin or matte finish. This is the preferred finish for the vast majority of surgical instruments. The surface is less reflective, which absorbs some light. This reduction in glare prevents eye fatigue for the surgical team, making it safer for long procedures. The trade-off is that the satin finish is slightly more prone to staining than the mirror finish, requiring careful cleaning. The third is the ebony or black finish. This unique black surface is used specifically for instruments involved in laser surgery. Safety is the primary driver here. A shiny instrument could reflect a laser beam, potentially bouncing it off the instrument and burning patient tissue outside the surgical site or damaging the eyes of the staff. The black finish absorbs the light energy, preventing the laser beam from reflecting. Therefore, if you see a black instrument, you know it is designed for laser procedures. Understanding the material is only the first step. To effectively inspect an instrument, you must understand its architecture. Most hinged instruments, such as hemostats and needle holders, share 5 structural components. You must inspect each part specifically and sequentially. The first component is the jaws. This is the working end of the instrument that comes into direct contact with the patient. When inspecting the jaws, you must ensure the tips align perfectly. If the jaws are serrated, the teeth must mesh together without overlapping. Misaligned jaws can cause tissue trauma. The second component is the box lock. This is the hinge point where the 2 parts of the instrument connect. It is physically the weakest part of the instrument and susceptible to breakage. More importantly, for a sterile processing technician, the box lock is the most difficult area to clean. It is the #1 hiding spot for cracks and hidden blood, known as bioburden. You must inspect the box lock for stress cracks under lighted magnification every single time. The third component is the shanks. These are the long, thin body sections connecting the box lock to the rings. The length of the shank determines the surgical reach, allowing the surgeon to work in deep cavities or superficial sites. You must check the shanks for bends or misalignment, as a bent shank will prevent the jaws from closing properly. The fourth component is the ratchets. Located near the rings, this is the locking mechanism that holds the instrument closed. To verify safety, you must perform the ratchet test. Close the instrument on the first ratchet, which is the first click. Hold the instrument by the box lock and gently tap the finger rings against a table. The instrument should not spring open. If it does spring open, the ratchet is worn out. This instrument is dangerous because it could spontaneously release a clamped vessel during surgery. The fifth component is the finger rings. These are the loops used by the surgeon to manipulate the device. Inspect them for cracks or loose plating that could harbor bacteria. Before we discuss specific instrument families, we must distinguish between instrument grades. Not all steel is created equal. Surgical-grade instruments are made of high-quality steel, usually imported from countries like Germany. They are reusable, designed to withstand repeated sterilization, and typically have a matte or mirror finish. In contrast, floor-grade instruments, often called economy or Pakistan grade, are made of lower-quality steel. They often have a shiny mirror finish but rust very quickly. These are intended for single-use or limited use in clinics, not operating rooms. You must never process floor-grade items in the same set or ultrasonic cleaner as surgical-grade instruments. The rust from the floor-grade item can transfer to and permanently damage your expensive high-quality inventory. Now, let us examine the classification of surgical instruments, starting with the most common family, hemostatic forceps. Hemostatic forceps, often simply called hemostats or clamps, are primarily used to occlude, or clamp, arteries and veins to stop the flow of blood. This process is called hemostasis. They can also be used to grasp tissue. Structurally, they feature ring handles, a box lock, a ratchet, and jaws. Identifying the specific type of hemostat requires you to look closely at the jaws. This is known as the serration rule. First, cryoforceps have serrations that extend along the full length of the jaw. Second, Kelly forceps have serrations that extend only halfway down the jaw. Third, mosquito forceps are small, delicate hemostats, usually fully serrated, designed for occluding small vessels. Fourth, Rochesterpian forceps are heavy, large hemostats with full serrations, used for heavy tissue or large vessels. When inspecting any hemostat, follow the protocol we just discussed. Check the box lock for cracks, as this is the most common failure point. Verify jaw alignment to ensure the tips meet perfectly and serrations mesh without overlapping. Finally, perform the critical ratchet test on the first click to ensure the device will hold securely during the procedure. Closely related to hemostats are needle holders. While they look similar, their function is distinct. Needle holders are designed specifically to grasp and drive curved suture needles to close surgical wounds. Because pushing a needle through tissue requires significant force, the jaws of a needle holder are generally shorter and sturdier than those of a hemostat to provide the necessary leverage. A critical feature you will encounter on high-quality needle holders is the presence of tungsten carbide inserts. Tungsten carbide, or TC, is an extremely hard metal. You can visually identify these instruments immediately because they have gold handles. The jaws of these instruments are not solid stainless steel. Instead, a pad of tungsten carbide is soldered onto the jaw. This material is harder than steel and lasts much longer. The inner surface of these jaws features a diamond-cut crisscross pattern designed to prevent the needle from rotating or slipping during suturing. To inspect a needle holder, you must check the jaw surface for wear. If the diamond-cut pattern is worn smooth, the needle will slip, causing frustration and delay for the surgeon. You must also perform the light test. Close the jaws tightly and hold the instrument up to a bright light source. You should see no light shining through the jaws. If you see light coming through, it means the jaws are worn and are not making full contact. In this case, the inserts need to be replaced. Moving on to the next category, we have tissue and dressing forceps. In the sterile processing environment, the term forceps typically refers to non-ratcheted thumb forceps that resemble tweezers. Surgeons and staff often refer to these colloquially as pickups. We divide these into two distinct types based on their tips. First are tissue forceps. These instruments are equipped with teeth at the distal tip. A common configuration is 1x2 teeth, read as 1x2, meaning one tooth on the top jaw fits between two teeth on the bottom jaw. The function of these teeth is to penetrate the tissue to provide a secure hold on skin or tough muscle. Common examples include the Adson with teeth or the rat tooth forceps. When inspecting these, you must ensure the teeth mesh perfectly. If they overlap or cross over, they will pinch and traumatize the tissue rather than holding it securely. Second are dressing forceps. Unlike tissue forceps, these do not have teeth. Instead, they have horizontal serrations at the tip, similar to a hemostat. They are used to manipulate dressings, pack wounds, or handle delicate tissue that should not be punctured. Examples include the plain Adson or smooth forceps. Your inspection focus here is proper alignment and ensuring the proximal end, or the handle end, is not cracked from stress. The next major family of instruments is retractors. As the name implies, retractors are used to move tissue, organs, or muscle aside to expose the surgical site for the surgeon. We categorize these by how they are held. Handheld retractors must be physically held by a surgical assistant during the entire procedure. Common examples include the Richardson, Sen, Army Navy, and ribbon or malleable retractors. Self-retaining retractors feature a mechanical action, such as a ratchet or a spring, that allows them to stay open on their own without human assistance. This frees up the hands of the surgical team. Examples include the Whitelawner, Gelpi, and Balfour. Inspection of self-retaining retractors requires extra attention. You must check the mechanical action to ensure the ratchet holds securely under pressure. For instruments like the Gelpi, which uses a spring, you must ensure the springs have sufficient tension to hold the wound open. If the spring is weak, the retractor will collapse during surgery. From retraction, we move to the precision instruments used for dissection. Scissors are used for cutting tissue, suture, or dissection. Because they rely entirely on the integrity of their sharp blades to function, they have the most specific and rigorous testing protocols of all instruments. There are 3 primary types of scissors you will handle daily. First are Mayo scissors. These feature heavy, sturdy blades and are designed for cutting tough tissue like fascia or heavy muscle. Second are Metzenbaum scissors. These are much more delicate, with thin blades and long shanks, used for fine tissue dissection where precision is paramount. Third are Iris scissors. These are very small, extremely sharp scissors originally designed for eye surgery but now used for detailed work in many specialties. Just like needle holders, scissors use a color coding system to tell you about their material and edge type. As before, gold handles indicate tungsten carbide or TC blades. These blades are extremely hard and maintain their sharpness significantly longer than standard stainless steel scissors. A different category is identified by black handles. These are known as supercut or microgrind scissors. These are unique because they feature one blade that is ground to a razor-sharp knife edge, while the opposing blade has fine serrations. This design allows the serrated blade to hold the tissue in place while the knife edge slices through it, resulting in a cut with minimal tissue trauma. Testing scissors for sharpness is a critical skill you must master. Rule number 1 is absolute: never use paper to test surgical scissors. Paper is abrasive. It creates paper dust and effectively dulls the blades you are trying to test. Instead, we use specific testing materials based on the size of the instrument. For scissors that are 4.5 inches or larger, such as Mayo scissors, you must use red or sometimes orange testing latex. The test procedure is precise. You must cut through the material all the way to the tip. The cut must be smooth and effortless. The scissors should not snag or chew the material at any point. To be certain, you must perform this cut 2 to 3 times. For scissors smaller than 4.5 inches, such as Iris or tenotomy scissors, the red latex is too thick. Instead, you must use yellow testing latex, which is thinner and appropriate for delicate blades. Finally, for laparoscopic scissors, which are long and delicate, the standard test is slightly different. You test these against a single layer of facial tissue or specific testing material provided by the manufacturer. If the scissors tear the tissue rather than slicing it cleanly, they are dull and must be removed for sharpening. While scissors cut tissue to reveal the site, the surgical team also needs a way to clear the field of blood and fluids. This brings us to suction devices. These are cannulated, or hollow, instruments. We will focus on the 3 most common types found in surgical trays. The first is the Fraser suction. This is a thin, angled tube used primarily for neurosurgery and delicate procedures where space is limited. A critical component of the Fraser suction is a thin metal wire known as a stylet. During surgery, the narrow lumen of the tube can easily become clogged with bone or tissue. The surgeon uses the stylet to clear this obstruction. For the sterile processing technician, the stylet presents a challenge because it is easily lost. You must verify that the stylet is present and kept with the instrument during assembly. The second is the pool suction. This is a straight tube that comes with a detachable outer guard or sheath featuring multiple small holes. It is designed for abdominal surgery, also known as laparotomy. The outer guard is a safety feature. It disperses the suction force so that delicate organs, like the bowel, are not sucked into the tube and damaged. When processing a pool suction, you must remove the outer guard to clean the inner tube effectively. If you leave it assembled, the area between the tube and the guard will remain contaminated. The third is the Yankauer suction. This is a curved tube with a bulbous tip, primarily used for throat suctioning during anesthesia or oral procedures. For all suction devices, the inspection priority is the interior lumen. Because you cannot see inside, you must verify the lumen is patent, or clear. You do this by holding the tube up to a light source to see if light passes through, or by flushing it with water to ensure fluid flows freely. Moving from soft tissue to hard structures, we encounter bone cutting instruments. This category includes robust tools designed to cut, bite, or shave bone. We divide these into two main groups based on their action. The first group includes osteotomes and chisels. These are used to shave or cut bone, often with the aid of a mallet. Because they must cut through hard bone, their edges must be sharp. The testing protocol for these is specific. You must use a plastic dowel rod. Place the cutting edge against the rod and apply pressure. The instrument should bite into the plastic and shave off a piece. It should not slide over the surface. If it slides, the edge is dull and requires professional sharpening. The second group is the rongeurs. These are heavy-duty instruments with sharp, cup-shaped jaws used to bite away chunks of bone. We classify rongeurs by their hinge mechanism. A single-action rongeur has one hinge. A double-action rongeur has two hinges. The double-action design is mechanically superior for heavy work because it multiplies the force applied by the surgeon's hand, significantly reducing fatigue during long procedures. A specific type of rongeur you must know is the Kerrison rongeur, often used in laminectomy or spinal surgeries. It features a unique design with a sliding shaft. This shaft is a notorious trap for bioburden because bone debris and tissue get wedged between the sliding metal plates. You must inspect this area aggressively. If the specific model allows, it must be disassembled for cleaning. If not, it must be carefully flushed under the rail to ensure no debris remains. Testing rongeurs requires a different material than osteotomes. For rongeurs, specifically the cup jaws, you test for sharpness using an index card or card stock. When you take a bite of the card, the instrument must cut a clean hole. It should not tear the paper or snag. If the paper tears, the jaws are dull or misaligned. Moving away from bone instruments, we encounter specialized tools for other procedures. You must be familiar with vaginal specula, which are self-retaining retractors used to visualize the cervix. There are two primary types you will identify by the shape of their blades. The first is the Graves speculum, which features wider, duckbill-shaped blades. The second is the Peterson speculum, which has narrower, flat blades designed for patients with narrower anatomy. A critical safety check involves specula used for LEEP procedures. LEEP stands for Loop Electrosurgical Excision Procedure, which uses electricity. Therefore, these instruments have a special non-conductive coating, usually blue or black, to insulate the metal. You must inspect this coating for scratches, chips, or pinholes. If the coating is compromised, electricity can escape through the defect and cause severe burns to the patient's vaginal tissue. If you see any damage to the coating, the instrument is unsafe and must be removed from service. Another specialized instrument found in podiatry or orthopedic sets is the nail nipper. These are heavy-duty cutters. Your inspection must check 3 points. First, check the cutting edge for nicks. Second, check the hinge or screw to ensure it is tight. If the blades are loose, they will not cut effectively. Third, check the spring tension. These instruments often use a barrel spring or a leaf spring to reopen the jaws. If the spring is broken or weak, the instrument will not function. We now arrive at one of the most technologically critical sections of this chapter, advanced inspection protocols. As surgery becomes more high-tech, our inspection methods must evolve to match. The most important of these is laparoscopic insulation testing. Laparoscopic instruments are used for minimally invasive surgery. They are long, thin devices inserted through small ports in the patient's body. Most of these instruments are connected to an electrosurgical unit or ESU to cut or cauterize tissue using electricity. Structurally, these instruments feature a conductive metal core covered by a layer of insulation, typically plastic or ceramic. This insulation protects the surrounding tissue from the electrical current flowing through the instrument. The hazard here is invisible but deadly. If there is a microscopic pinhole, crack, or tear in this insulation, the electricity will escape from that point instead of traveling to the tip. This leaking electricity can burn nearby organs, such as the bowel, that are touching the shaft of the instrument. Crucially, this often happens outside the surgeon's field of view on the monitor. This is known as a stray current burn. The surgeon may never know it happened until the patient develops a severe infection days later. Therefore, the testing requirement is strict. Visual inspection is absolutely not sufficient because many defects are too small to be seen with the naked eye. You must use an electronic insulation tester, often called a lap tester, every single time the instrument is processed. The test procedure involves 4 steps. First, the instrument is connected to the tester unit. Second, a specialized wand or collar is passed slowly over the entire length of the insulated shaft. Third, if the tester detects a break in the insulation by completing the electrical circuit, it will trigger an audible alarm or beep. Fourth, if the alarm sounds, the instrument has failed. It must be removed from service immediately and sent for repair. There is no margin for error here. A failed insulation test is a direct patient safety threat. In addition to electrical hazards, we must also manage magnetic forces in the operating room. Surgical instruments can become magnetized over time due to exposure to magnetic needle counters, magnetic instrument mats, or even the friction of the machining process itself. The problem with a magnetized instrument is not just a nuisance, it is a safety risk. If a needle holder or tissue forceps becomes magnetized, it can cause a suture needle to jump out of position or stick firmly to the instrument. This makes it incredibly difficult for the surgeon to control the needle precisely, which is especially critical in microsurgery where movements are measured in millimeters. Testing for this condition is simple. Place the instrument near a standard paperclip. If the paperclip sticks to the instrument, it is magnetized. To fix this, the instrument is passed through a device called a demagnetizer. This device uses a coil-based mechanism to generate an alternating magnetic field. By passing the instrument through this field, the magnetic alignment in the steel is neutralized, restoring it to a neutral state. Beyond maintaining the metal, we must also maintain the identity of the instruments. Because thousands of instruments look nearly identical, facilities must have a system to identify which instrument belongs to which specific set or specialty. This brings us to instrument identification and marking. There are 4 approved methods and 1 strictly prohibited method. The first and most common method is tape, often referred to as color coding. There is a strict protocol for applying tape. It must be applied to the shank of the instrument only. You must never apply tape to the finger rings because it is impossible to clean underneath the tape in that area, allowing bacteria to hide. You must also never apply it to the working tips, as this interferes with function. When applying the tape, it should wrap around the shank 1 to 1.5 times. If you wrap it too many times, the tape becomes thick and creates ridges that harbor soil. Inspection of taped instruments is mandatory every time they are processed. If the tape is peeling, chipping, or cracking, it must be completely removed and replaced. Loose tape is a major hazard because it can fall off into a surgical wound, becoming a foreign body inside the patient. The second method is acid-base etching. This is a chemical process used by the manufacturer or a repair vendor to mark the instrument with text or logos. It is permanent and safe, provided the chemicals are properly neutralized after application so they do not corrode the steel. The third method is laser etching. This is the modern standard for durability. It is used to apply 2D data matrix codes, which look like square barcodes, allowing for computerized instrument tracking systems. Importantly, laser etching does not damage the passivation layer of the steel. The fourth method is color bonding or dipping. This involves applying a colored polymer coating to the handle, similar to a powder coat. Like tape, this coating can chip and peel over time, requiring rigorous inspection to ensure no flakes are loose. Finally, we must discuss the prohibited method, engraving. As a technician, you should never use an engraving tool or a vibrating tip to mark instruments. Think back to our lesson on manufacturing. Engraving physically scratches the surface of the steel, which destroys the passive chromium oxide layer we discussed earlier. Once this layer is broken, you have created a permanent breeding ground for rust and bacteria that cannot be fixed. Therefore, mechanical engraving is strictly forbidden. Once instruments are inspected and marked, we must focus on their long-term care. The primary method for maintaining hinged instruments is lubrication. Hinged instruments have metal-on-metal friction points that grind together every time the instrument is opened or closed. Over time, the passive layer in the box lock wears down, leading to stiffness and corrosion. To prevent this, we use a lubricant commonly called instrument milk due to its white, milky appearance. There are strict rules for this product. First and foremost, the lubricant must be water-soluble. You must never use oil, grease, or hydrocarbon-based lubricants like WD-40. These substances are not water-soluble and will form a barrier that blocks steam from reaching the surface of the instrument, resulting in a non-sterile device. The application process is unique. Lubrication is performed after cleaning and before sterilization. Unlike detergents, instrument milk is generally not rinsed off. You dip the instrument, remove it, and allow it to dry. The goal is to leave a thin, protective film on the metal that lubricates the hinge during sterilization and storage. Conversely, there are substances you must strictly avoid. You must know which solutions cause irreversible damage to your inventory. First is saline. Never soak instruments in saline. Saline contains chloride ions that aggressively break down the passive chromium oxide layer, causing pitting corrosion. Second is bleach. Sodium hypochlorite causes severe pitting and corrosion on stainless steel. High-level disinfectants containing chlorine are generally contraindicated for surgical instruments. Third is betadine or iodine. If used in the operating room, it must be rinsed off immediately, as it causes staining and pitting. Fourth are dish soaps or laundry detergents. These should never be used. They contain whiteners and fragrances that are difficult to rinse off. These residues can cause spotting on the metal and, more dangerously, can cause pyrogenic reactions, meaning they can induce fever in patients. Only professional medical-grade detergents should be used. After maintenance comes assembly. Errors made in the preparation and packaging area directly affect the surgery. We must follow 3 key rules for tray assembly. Rule 1 is heavy on bottom. When assembling a tray, always place heavy items like retractors and mallets on the bottom. Delicate items like scissors and tissue forceps should be placed on top. If heavy items are placed on top of delicate ones, the delicate tips will be crushed or bent. You must also avoid dumping instruments onto the table, as the impact can fracture box locks or misalign jaws. Rule 2 is stringing. Hinged instruments must be placed on a stringer or U-holder. Crucially, they must be strung in the open or unlocked position. This is mandatory. If an instrument is closed, steam cannot contact the surfaces of the box lock or the jaws, and those areas will not be sterilized. Rule 3 concerns ratchet locks. When placing instruments on a stringer, do not lock the ratchets tightly. During the high heat of steam sterilization, metal expands. If the instrument is clamped shut on the last ratchet, the metal has no room to expand. This built-up pressure will cause stress cracks in the box lock. Therefore, allow the instrument to remain slightly loose. Finally, avoid mixing metals. Do not place stainless steel instruments in the same ultrasonic cleaner or tray as instruments made of other metals, such as chrome, brass, or aluminum. When different metals touch in a wet environment, a reaction occurs called galvanic corrosion, or electrolytic corrosion, which transfers rust and damage from one instrument to the other. Beyond the arrangement of instruments, you must also control the density of the tray. This leads us to the prevention of wet packs. A wet pack occurs when moisture remains inside the tray or packaging after the sterilization and drying cycle is complete. To prevent this, you must avoid tray clutter. Do not overload trays with too many instruments or stack them too high. If a tray is too dense, the metal mass absorbs too much heat, creating excessive condensation, and the steam cannot circulate effectively to dry the items. This results in a wet pack. You must understand that a wet pack is considered non-sterile. Moisture acts as a vehicle, allowing bacteria from the outside environment to wick through the packaging and contaminate the instruments. Therefore, any wet pack must be rejected and completely reprocessed. We also need to discuss physical protection. Sharp instruments require specific safeguards. You must use tip protectors for items like osteotomes, skin hooks, and scissors. These protectors serve two purposes. First, they prevent the sharp tip from puncturing the sterile packaging paper. Second, they protect the delicate tip from being dulled by impact. Crucially, you must use only validated tip protectors designed for sterilization. These are typically made of materials that allow steam to penetrate. You cannot simply use any piece of plastic tubing. Special attention must be paid to laser finish instruments. As we discussed, these black instruments have a coating that absorbs light. You must protect this finish from metal-on-metal scratching. If the instruments are thrown loosely into a basket, they will scratch each other. Once the black finish is scratched, the underlying metal is exposed, and the safety feature is ruined. Finally, to function effectively in the decontamination and assembly areas, a sterile processing technician must be fluent in the language of the operating room. Count sheets often use common abbreviations to save space. You must memorize these to identify the correct items quickly. CVD or CR stands for curved, such as a curved cryohemostat. STR or ST stands for straight, such as a straight Mayo scissor. L or LG stands for large. S or SM stands for small. S/S stands for sharp/sharp. This refers to the points of a pair of scissors, meaning both tips are sharp. S/B stands for sharp/blunt. This means one tip is sharp and the other is rounded or blunt. TC stands for tungsten carbide, indicating the instrument has hard inserts or blades. CV stands for cardiovascular. This concludes the comprehensive audio lecture series for Chapter 10 Surgical Instrumentation. You have now covered the critical concepts of instrument metallurgy, the detailed anatomy of handheld devices, the specific inspection protocols for various instrument families, and the essential maintenance standards required to ensure patient safety. Your ability to act as a quality control expert is the final line of defense before an instrument reaches the surgeon's hand. Good luck with your exam and your career in sterile processing.